Good afternoon, everybody. Welcome to the seminar. Today, I'm going to talk about checkpoints. Give me a sec. Okay. So, not all jobs would succeed. So a job can fail when it happens. And if you don't implement some particular mechanism, you will need to resume the computation. That means all the previous computation that has taken, let's say, in hours, even days, are down the drain. So in this situation, checkpoints come into play. A checkpoint is a snapshot of the job status at a certain point of the execution process, so that later on you can resume from a checkpoint. So you don't have to resume from the very beginning. That's the idea. So there are several maybe multiple reasons that could trigger termination of a job. Either it's when there's a system glitch, or if you didn't request sufficient time for your job, or there's a bug and whatever. So there is always various reasons that could cause the early abortion of your job execution. Oh, so we have a wiki page which gives a general guideline how to implement a checkpoint, but I still see some users, are not so comfortable to implement their own checkpoints. So in this talk, I'm gonna, introduce checkpointing through two concrete examples. So I hope those examples will serve as templates that you can use to, either, adapt, customize them for your own computational jobs. So we're gonna cover using checkpoint in different scenarios, like in serial job, OpenMP and MPI. You can see the example. The two is one example is written in C, the other is in Python. So we also demonstrate how what the file type of the checkpoints could be either text file or binary. So I will show those very soon. Uh, I'm not gonna talk about non-interactive non-iterative jobs. So the type of jobs that I'm gonna address is the type of which contains a lot of which contain the time the iterative process, which is the major time consuming part. So some software packager has their own checkpointing mechanism, so you can follow their instruction to use them. So we are not going to cover those two types of scenarios. All right. So I'm gonna talk about the state of a iterative process on a case-to-case basis. And I'm gonna talk how to save and restore them. And you know that because snapshot is just a file that's saved on disk, and the disk I/O is much slower than the CPU speed. So you should consider the frequency of saving checkpoints. Otherwise, the overhead is too much, you know. And secondly, you can consider whether or not you are gonna save the file in the ASCII format or in binary format, or you are gonna just save one checkpoint or versus multiple ones. If you choose one checkpoint, that means you're gonna overwrite it whenever you need to write a new checkpoint, which I do not prefer because uh, right now the disk space is not issue at all. So I would prefer to save each individual checkpoint, you know, so that later on I can recover from whichever that I would like to. All right. How to implement the checkpoints? So first, like I said, I'm gonna focus on a job that is composed of explicit iterative process, which is a loop. No matter it's for loop or while loop, it's a loop. And uh, for those that build in uh, like a implicit iterative process, like training, you see whenever you use a keras fit, which contains a lot of iterative process inside, and you can register a callback. But this is out of the scope of this talk. So let's focus only on application and that contains a very time-consuming iterative process. So normally it looks like this. You have a initialization step, and then you enter a loop. And in the loop you do some calculation. So that's the typical structure. And how to make it, give me a sec. Uh, we can embed the checkpointing in two ways, in two places. When we save the checkpoint, we embed it in the loop. So you don't have to save a checkpoint for every iteration. Although I write it this way, but you should interpret it in other way. You can use some kind of frequency control, like say save a checkpoint every, let's say, 10 or 10 or 100 iterations. You save it in the disk. When the program failed, and next time you run the program again, you can load a specific checkpoint instead of resume from the very beginning. So that's how it works. Uh, let's take a look of first example to see how the idea is got implemented. So the first example is calculating the pi value, which is 3.14 something, okay? And from mathematics, we know it's an integral between 0 and 1 of this particular function, which is 4 over 1 plus x squared, okay? And if I plot it, it's something like this. You see this is the curve defined by this function. So from 0 to 1, when we do the integration from 0 to 1, which means we want to calculate the area under the curve between 0 and 1. And how to do that? We can do it in a numerical way, which is we divided the interval between 0 and 1 into multiple bins. So here, suppose we define into 10 bins. So the width of each bin, I call this step, is 1 over 10, which is 0.1. And for each bin, although originally the top is curved, but I approximated with flat top, which means I approximate each bin as a rectangle. For the first rectangle, the height is F0. Uh, then the height times step give me the area of the first rectangle. And I can do the same thing for the second and the rest. So using the function at different location as the height and do the multiplication. And then I have reformatted the expression. I can do the plus, the summation in a loop and do the multiplication just once instead of do the multiplication 10 times. So this can save a little bit of time. Okay. So I'm gonna use this formula. So first I do a summation of heights at different locations and then do the multiplication. All right. All right. So let's first take a look of the code. How how to do that? Is there a question or something? Oh, give me a sec. Sorry. Okay. Pi.c is very short. So I'm gonna so first of all, instead of 10, I'm gonna divided the interval into a big number. Here I think I divided into 100 million beans. So the more beans you have, the more accurate the result will be. Okay. So in this program, it's very short. You can see the main part is just a for loop. And in the initial step, you need to define, okay, I'm gonna use sum, the variable called sum to accumulate the heights. And I'm gonna start from 0. So basically, I'm do a for loop, loops of, for 100 million times. And in each step, I use the I to, to times the steps, give me the x coordinate. But why I use 0.5? This is not necessary, but I want to make it in the middle of that bin. So I got the x, then I plug the x value into the function that give me the height. Then I add this height into the sum, which is originally set to 0. Okay, so very simple. So after the for loop, I accumulate a lot of the summation of heights into this variable. And lastly, I type the summation with the width, which width of the bin that gives me the final result. Then I print it out. All right. So very simple one. I can run it. I already compiled it. So I compiled it use GCC. Basically, if you want to, you can use my README file. Uh, I just do the use GCC to compile it. So if I do this, I just run it on the login node. Normally, you shouldn't run any, very intensive computation here, but this is a very simple one. I just run it. I got my result. Okay, so this is the um, uh, uh, the serial code to compute pi value. Now look at it. how to implement a checkpoint in this code, as I showed in my program. Oh, sorry, not this one. Here you can see I needed to do some loading right after initialization before I enter the loop. And in the loop, I'm gonna to save the checkpoint. All right. So I follow the same thing. Let's look at the code. So the code for this one, I call it, okay, this one. I call it pi checkpoint text. Text means I'm gonna save the checkpoint as a plain text. Okay, so let's take a look of this code. So then you can take a quick look. You can see I define two helper function. One is called save checkpoint, the other called read checkpoint. And the main function is quite similar to the previous one, but with two insertions. One is the first part, just after initialization, I do some insertion of read the checkpoint. And in the loop, I add another insertion here, save the checkpoint. And I control the frequency like every n, n is a number. Every n iterations, I'm gonna save a check. Not every iteration, every n iterations. So how large is n? That take n is 1 million. So that means I still do 100 million beans, but once I loop through a million, I save a checkpoint. Okay, so here is where I am going to save the checkpoint file. I save it under a folder called checkpoints, and the file name is like this. And if you're familiar with C, you can see here is this part will be replaced with the integer number that I will show later. And then take a look of the first helper function called save checkpoint. It takes a file name where I'm going to save. And here I'm gonna save the iteration number and the summation. So here comes the question: what is the state of this particular calculation? So if you look at the code, this the for loop. If suppose you just imagine if it's interrupted somewhere in the middle, what's the state? What information you need to recover from where it's left? So first of all, you want to know where it's interrupted, which is I call it iteration number. And secondly, what's the current summation that I already achieved? So only those two. So that's why here I'm gonna save iterative number and the summation that has been accumulated so far to a file name, to a file with this name. So take a look. So first I open the file and I check if the file the opening succeed or not. If yes, I'm gonna write into the file with the file handle that I just opened. I only write two variables. The first one as an integer, the second one as a float. Integer is the iteration number, the float number is the summation. So that's it. When I recover it, I call it a read checkpoint. Basically the same thing, but you notice this one is a pointer. But as long as you know how it works with C, you know the concept of pointer. You know because here it will bring back the value that I'm going to read from this file. So this is a pointer instead of the variable itself. Okay, so the same thing. I open the file for reading. And then if succeed opening, I'm gonna read it in the exactly the same order. How you write it, you should read it in the same order. So I'm read the iteration number and summation back in exactly that order. After that, I'm closing it and return. Okay, so that's the two helper functions. So let's take a look of the main function. So the first part is suppose it failed. We already saved some checkpoints files. So you need to specify which check file you're gonna uh, restore from. So suppose I'm gonna start from the 19th checkpoint. So you specify. So you see here I'm comment out this section, but you can certainly uncomment it if you want to resume from the. So suppose we going to uncomment this part. So I'm gonna you select which checkpoint file you're gonna use, then you're not gonna use the read check file to read that file and recover start and the sum. And see those two files, two variables that you're gonna recover. But you see, if without it, what are those two variables are initialized? The start is initialized to 0, and the sum initialized to 0. Okay, but if you have some checkpoint file loaded, so you will have a non-zero start and a non-zero sum to start with. So for the for loop, instead of the previous where you see I equals 0, now it's not, it's from start. So start could be 0, could be some non-zero number, depending on whether or not you're loading the checkpoint file, okay? The rest part is quite similar, and we only need to look at this part where I'm gonna save a checkpoint for every n iteration, every annealing iterations. So what I'm doing is first I got the index from the iteration number, and I'm gonna create the file name based on the file pattern. Basically, I fill up the this part. I fill up this part with the number, and I'm gonna save call this function to save the iteration and the summation into the file. So that's it. That's what I'm doing. Okay, so let's run it to see what we have. Although, like I said, uh, I already compiled it. The executables like this. So I just run it on the login node because it won't cost too much, but don't do that very often. So it gives me some result and also prompt me that it saves 100 checkpoint files. So let's just pick up some of them to check the value, because here I just write the checkpoint in plain text so I can see, okay. So the first checkpoint I got is like this, 1 million. And this is the summation of heights. How about the second one? Um, if you take the second one, you can 2 million and you have another number. So that's it. So so that's how it works. But suppose you want to oh sorry, I give the wrong number. Okay, I give it. So let's do it again. Suppose we are gonna uh, use the checkpoint. Like I said, I'm gonna uncomment this section. Oh, sorry. I just uncomment it, save it, and I'm gonna compile it. Oh, let's go. So I'm gonna run it. This time I'm gonna run it from the breakpoint 19. Let's see how it works. So it runs very quickly, but you can see it starts from 19, loading the checkpoint 19 and starting from there. Yeah, so that's how it works. And because this is very simple and it's only for serial job. And now let's take a look of how to make it work uh, in other scenario like OpenMP. So this is the one. All right. So just a quick summary. So here the status, the state of the computation for this pi value is only iteration number and the summation of being heights. And next, I'm gonna look at the OpenMP code. So first of all, how to make the original one, the original serial version of the pi calculation into a OpenMP version. Take a look of this one. Basically, it's very simple. You just add some OpenMP directives, something like those things, and which tells the C compiler to make this block into a multi-threading implementation. Uh, so you don't need to specify details, and this part will be run in threading mode. Okay, so that means suppose you have 10 threads. So one thread take 1/10 of the computation or iterations uh, do the summation because they are quite independent each other, and eventually they sum them together into the master, and you got the use result. So I'm not going to explain the OpenMP derivative in details. You can check the mint. So it's basically very simple like this. All right. But now the question is, because this for loop now is gonna be run in threading mode, how to embed it, the checkpointing, the save checkpoint. So if you write it here the way like we add the checkpoint in the serial code, you got into trouble because every thread will do the saving thing, saving, and so which is not which is not what you want. You only want to save one. You don't want to save multiple checkpoints at a single execution point. So how to 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 to, to do this? One thing to do this is to break a single loop into a nested loop, something like this. So for example, here I have a single loop looping for 50,000 times. I'm going to break it down into nested loop. So the first loop is the outer loop is loop of 50 times, for example, 50 times, and the inner loop for basically 1,000 times. Altogether, they loop 50,000 times. So these two are quite equivalent. So once we have reformat this, we can use the OpenMP derivatives with only the inner loop, not the outer loop. So let's take a look of the code. So let's take a look of the code, this one. All right. So basically the same thing. I'm defining n as the control the frequency which means I'm gonna loop every 1 million. Every 1 million uh, iterations, I'm gonna save one uh, checkpoint file, and I'm gonna run 100 times, this is the outer loop numbers, and yeah, so you time them together, you got the overall number of loops. Okay. And basically the same thing as before, and the same save checkpoint function, and the same read checkpoint function without any alteration. And let's take a look of the main function of this OpenMP version implementation of the checkpoint. So the restoration is the same without change if you want to restore it. The only part, I think that this is the part that you need to focus on. So I create the outer loop, which loop number of batch, which is 100. I can start either from 0 or from a non-zero. If it's non-zero, that's because I'm uncommon this part, and after that, the outer start the start, I recovered a non-start iteration number, and from that iteration, I converted to how many you know uh, millions. It's called in terms of just like unit. How many? If 3 million, this should be 3. So that's something that you are going to do. And then for the inner loop, I put it into this directive. So that means the following block will be in OpenMP parallelism. And I have two portions. This part for the for loop that I'm gonna do, and the second part I'm gonna save. Remember, when I do the save, I'm not going to let each thread do a saving. I'm only let the master do. So that means I only do it once. Okay, so that's the only part, the only difference. All right, so very simple one, not very complicated. So I'm not gonna run this one because I will let you have the code. You can download them, you can play with yourself. All right. So like I said, I don't think I have sufficient time to do everything. For the MPI version, I'm gonna skip it because it takes time. But basically, for MPI code, you need explicitly distribute the computation by yourself. So here, there's many ways to dispute it, such a large loop, among, let's say, 10 or 100 processes. Uh, you can either, let's say, suppose you create 100 processes. You can like the first process working on the first million iterations, and the second process working on the second million iterations in that way. But I'm gonna do it in another way, in a uh, alternating way, which is suppose we have three processes. Uh, I'm gonna do, if I use this one, you can see here I'm use I plus, first of all, it start from the current process ID, which is from zero based integer. The first one is 0, then 1, 2, 3, until the last one is the number of thread minus 1. So I'm going to jump every, for this one, 3, I every jump. So every 3 element, I'm going to assign to the process 0. And for the process 1, I do the similar thing, but starting from the position, the second position. And the same for the 2, I can do the quite evenly distributed the computation among 3. So in this way. But I'm gonna introduce this in much detail. But anyway, so far, you see that what we have done is, we save uh, the state, which are 2 variables, into a file, a plain text file, and we do it. We must keep them in the same order. If we do the iteration and summation, we write it in that way, and we read it in the same order. But imagine if you have a more complicated data structure that you want to save as a state. Uh, Certainly, you can do it in the same theory. You write, for example, account number integer, account type, probably you can also use integer, and then you jump name like string, age like integer. This is, you can use like either integer or Boolean or whatever. An occupation could be enumeration or integer, and a balance as, let's say, a float point, intrinsic float point. So you have your own order. You write them, one by one, and then you read them in the same order, just as I illustrated in the first example. But it's so boring. We hope that we have a better way to handle a structure like this, and this comes to using the non-plain text form. You can choose either um, uh, you know uh, you can use either a JSON type, or you can use some programming specific format like a pickle, which is unique to Python. I'm gonna just demonstrate another example now. So this example is how to generate a Fibonacci sequence. The Fibonacci sequence is like this. You have start with a 0 and a 1, and then the next number is the summation of the previous one. So 0 plus 1 is 1, then 1 plus 1 is 2, and the 1 plus 2 is 3, and the 2 plus 3 is 5, and so on and so forth. You get your numbers. So the first row is the Fibonacci sequence that I'm gonna to generate. So in the start, I said, okay, I must have two numbers to start, 0 and 1, and I'm starting position is 2. So that's the state of this computation. So when I come, for example, I'm come to this point, let me see if I can use some notation. Yeah, I can use the notation. Suppose I come, I have complete the 5, and at this point, it suddenly the program failed for either system glitch or whatever. And then I have to remember the last two numbers, 3 and 5, and the current position 6, that I'm going to start to calculate the next one, which is 6. So these are the states. So we have iteration number plus two number in the sequence. Okay, so that's the states. Let's delete those, create those. All right. So that's how we do it. How we generate it, and we will show how to do it in 3 ways. One is in plain text or that JSON file, and the last one in Pico format. So let's see the example. So first, take a look of the original one. Very short. So I have initially I have the last two numbers 0 and 1. I'm gonna start from 2. I'm not going to generate unlimited sequence. I'm gonna stop after I generate 1,000 Fibonacci numbers. Okay. So for this one, it's very simple. I'm gonna loop from the start until the end. And there's only one meaningful calculation. I calculate the next one, and I'm gonna print the next one, and then I'm gonna do some replacement, update the last two. Last two are a list. Remember the last two. So I have to move the 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 the, the this one into because I have to update them. So the new calculated the number will be in the second position. The second one in the list will be put in the first one. So very simple one. So let's run it. Probably I should load SciPy stack. And I'm gonna pass on just this code. So it's a lot of numbers. So probably the first few may be more readable. Oh, let's see if I can move this one. Okay. Yeah. So the first few looks then become bigger and bigger. But anyway, this is how I show it. Okay. And this is the code. And how to this is the original code. How to write it in a text file? Pretty simple. Let's look at this one. So I similarly define a save checkpoint and read checkpoint file in the Python version. Basically the same idea. And once I have those two functions, that I'm gonna do exactly as what. So the first step, I can either, I have two options. I can right now I comment out this this part. So I'm not gonna load any checkpoint, which is my option one, skip the loading checkpoint. In the initially, when there's no checkpoint, you can certainly do just skip. Okay. Then if you want to load, you can either use option two or option three, or which is either read a specific one, like I do here. I read the first one, I can specify the number here, or you can use option two, check all the available checkpoints and only load the last one. So right now, as I comment up the option two, basically I'm running option three. I didn't comment up this part. So, but in the very beginning, there's nothing there. It only pick up the uh, uh, it won't load anything if there's no checkpoints. So after I load the checkpoint, I only have a new start and a new last two. And in the very beginning, the start from two and the last two are filled with zero and one. So that's it. So very simple. And also in the for loop, I have a saving mechanism. I save every n is I mean every million iterations. I'm gonna save it into the file calling the save checkpoints. So very similar to previous function. So I'm not gonna run it. So let's take a look of the JSON version, how to save it into JSON. So first of all, you need to import JSON package or module. And basically, it's the same thing as before. The main function is the same. You don't need to change anything. And the only thing you need to change is how to define the save and read checkpoints. You can see here, what I'm going to do is I open a file and the same thing, but I'm using JSON dump. Here you can see I dump a state. What state? State, I define a new variable, which is a dictionary. So the first one is for dictionary, for the key, I call it iteration. I have iteration number. And the last two, I have a list, which is last two. So I have a readable thing, it's, so here I use dump, and then when I recover, I use JSON load file. I return a state. When I return it, I just grab, I extract the two variable from the state using the key. The first one called iteration. The second one I call the last two, so I can get them back. So you compare with the plain text. The previous one, I saved the two variables here as a two separate one. So imagine you have a very complicated structure. You have a lot of variable here, so it's not nice. But here I just organized in a more readable structure, either dictionary or some other structure, and I just use JSON dump, and so easy, eh? So it's good. And lastly, let's take a look of the Pico file. Pico file is a specific structure unique to Python. It's not available in other programming languages. But for other languages, if you want to use some special structure, you can certainly explore other options by yourself. But here I just demonstrate how to use Pico. I'm gonna use Pico in the original way without any fancy stuff, but you can certainly, use Pico with some either gun zip or some other compression scheme. There's tons of example of doing that, but here I'm not going to show that. So like the previous example, the Pico version, you only need to change these two files, save checkpoint and the read checkpoint. So basically you can see here, you open a file, use WB means that you are gonna save because this is a binary file and you have the same states as a dictionary, and you use pico dump. And when you read it, you open a binary file for reading, and you use pico load, and similar to previous one. So yeah, so I'm not gonna run those example because of time, but I can certainly show you the code. I have written some for the Fibonacci. I combined the three versions, one for text, one for JSON, one for Pico. I combine together. So basically, you just need to load the SciPy stack because it contains the packages that I need, like NumPy or JSON or something else. So you load them and you just run them. So very simple, and the result, the checkpoint are saved in this directory. So if you want, you can see I already run them. So checkpoint, Fibonacci, I just do you see a lot of them there. Yeah. And yes, for the other one, for the high value calculation, I have another job script. You can see something like this. You just run it. Yes. So yeah. So I'm sorry that I do not have sufficient time to cover the Pi MPI version, how to implement into checkpoint into MPI. But as I mentioned, the same idea, first you need to break the single loop into a nested loop, and then you just work on the inner loop. And that's it. So you can take a look of the code, and the code is, you know, is loadable from this link that I'm gonna give these slides to you for so from there you can find the link to the code. And finally, let me see where we are. Okay, so okay, I finished the second example. So some discussion about checkpoint, whether or not you're gonna. So first of all, text file is readable. You can display them. You can see them. JSON file is even better. It's text file, but with those keys inside. You can see the value and some kind of description there. For compression or a binary format, it's not readable anymore. But the good thing is, if the checkpoint is very large, binary, especially the compressed format, is preferred to save space. And for single or multiple, like I said earlier, I prefer multiple. So it's later on you can resume your computation from any those available checkpoints. And also, if you choose a single checkpoint, it's very dangerous uh, because suppose you are in the process of overwriting the current checkpoint. Uh, just at that moment, there's a system glitch. The writing operation just halfway, and you got a corrupted, you know, checkpoint. You are not gonna to resume anymore. With multiple checkpoints, you don't have such risk. Suppose the last one was corrupted, you still have the second last one. And regarding the frequency, that's up to you. Like I mentioned, uh, saving a checkpoint to disk consume times. So you have to choose the frequency. And what if a checkpoint is corrupted for some reason? If suppose you only have one, you can, if it's a text file, you can certainly based on your knowledge to correct some of them, but for binary, probably you have no way to recover them. And that's it.